This is question 4 from the 2019 AQA AS paper 2. Pretty sure this is the last long answer question on this test. It's multiple choice after this. So this here is a question that says it's about the initial motion of a boat and trailer when pulled up the ramp as shown in figure 8. The boat and trailer are pulled by a motor which is connected to a 24-volt battery with negligible internal resistance. So, the motor is shown, it's switched on at time t equals 0. Determine the total energy input by the 24-volt battery in the first 200 milliseconds. So, we're going to make one assumption. We're going to make the assumption that it's 24 volts the whole time. So, what we need to have is current times voltage times time. Well, this is a constant, and I times t. Well, I've got I, and I've got t here in milliseconds. Boy, what do I do when I want to find the multiple of two things that are on a graph? Ah, right. I need to find my area under the graph. Okay, so, oh, that's probably irritating some people. And 30. Okay, so that's about 31. This is 32. That and that is 33. This and this is 34. Yeah, it's 35 and a half, we're going to say. That we're at, I can estimate 1, 2, 3, 4, 5, 6 of them. So what am I really missing from this? That's about 2/5. Yeah. I don't really want to count small squares. Well, that's basically 1. Gonna make that about 3.5. That's 0.6. That's 0.6. So we're looking at about 40, between 40 and 41 boxes. So I'm going to go 40.5 boxes. Each box is 0.025 seconds and 10 amps. Good Lord, that's a lot of current. So I would go, my I times T is 40.5 times 0.25 times 10 is equal to 10.125, or sorry, times 24 volts. Uh, 243 watts, or 243 joules in the first 200 milliseconds. And let's check our mark scheme, and yep, that's within the accepted range. The range is actually pretty big, so my hemming and hawing about what was half of a square and 0.6 was not really that big of a deal. If you don't count the squares, but do like a trapezoid method or whatever, you'll still end up in the range as long as you have sort of recognizable shapes. You do need to show your method for this. You can't just plop down a number because the answer depends on your technique. They are not really like, yes, they care about the final answer, but what they care about is your technique. Do you know what you were supposed to do, and you're not just taking a wild guess? Okay, so the boat and trailer are initially at rest. First 200 milliseconds, the boat and trailer are raised vertically through a height of 3.3 times 10 to the minus 2 meters, and the speed increases to 0.85 meters per second. Assume that all the useful energy output of the motor is transferred into kinetic energy and the gravitational potential energy of the boat and trailer. Determine the average efficiency of the motor during these first 200 milliseconds. Well, so energy of the boat is equal to the gravitational potential energy and the kinetic energy. So mgh plus 1/2 mv squared. Sorry about that. I couldn't get to the mute button in time. Mgh plus 1/2 mv squared. So 180 times 9.81 times 3.3 times 10 to the minus 2 plus 0.5 times 180 times 0.85 squared. Okay, actually let's try it back with the calculator one. So 180 times 9.81 times 3.3 times 10 to the minus 2, it said, right? Yep. Plus 0.5 times 180 times 0.85 squared is 123 joules. So my efficiency is useful energy in divided by the total energy, useful energy out divided by the total energy in. So efficiency is 123 divided by 243. Now it's fine if this number that you're using is different than the one that I've got, because as long as you're using your answer, you have to use your answer from question 4.1. Okay, 123 divided by 243, 0.51. Okay, so it's about 50% efficient. Remember, when you're doing efficiency, you can either write it as a percentage or as a decimal. It should not matter, because it doesn't say percentage efficiency or anything like that. Okay, and the last bit of our question. So either of the circuits shown could be used to reduce the initial surge current. A thermistor and the fixed resistor have the same resistance when they're at the same temperature of the surroundings. When the surge has ended, the boat and trailer continue to move at a constant speed. To the top of the explain why, with reference to properties of thermistor and fixed resistor, why using the thermistor is preferable to using the fixed resistor. So the fixed resistor, so this one here, okay, so it's going to have a constant R, so you're going to have a lot of energy, basically a constant amount of energy that's being dissipated, meaning your efficiency is basically fixed. Okay, however, both of these are going to heat up. Okay, no, flows, not falls. As I flows, the how am I going to write this? The resistors heat up. Okay. Okay, so since the resistors are heating up, okay, that doesn't affect that one, okay? However, the thermistor resistance is going to decrease, and since P equals I squared R, okay, the thermistor is going to be more efficient. Ugh. No, not a highlighter. Eraser. Okay, so basically you'll have less wasted energy in the thermistor, which means that you will have the battery's going to last longer. It's not going to have to output more current for the same amount of power. Yeah, that's basically it. So we're going to have less wasted voltage, we'll have less wasted current, less wasted power, all of that. But the whole point is that because it heats up, the resistance will drop, and therefore we will end up with a more efficient circuit. Okay, that should do it for question 4.